The cost of running these really complex AI workloads in the cloud, everything from training those huge foundational models to handling real-time inference. It's not just another line item anymore. It's actually becoming a serious strategic business risk. We're seeing it again and again. Enterprise cloud bills, especially the ones heavy on GPUs and TPUs, they're hitting, frankly, shocking levels. It feels like every single architectural choice an engineering team makes is now, well, fundamentally a core financial decision.
That's exactly the inflection point we're seeing.
Yeah.
When you consider just how fast teams are adopting and scaling up this premium compute hardware, you just can't treat cost optimization as something you look back on, weeks later, something for a separate finance team to sort out. The architecture itself has to be cost aware right from the very beginning.
So today we're diving deep into this. We've curated this deep dive specifically for you, focusing on that critical intersection of cloud architecture, financial operations, FinOps, and intelligent resource scheduling. We're going to look at this whole challenge through three different but totally interdependent viewpoints. There's the cost ops analyst whose job is to track every single dollar and make sure costs get attributed correctly. Then there's the framework maintainer who's optimizing the underlying infrastructure itself for efficiency. And finally, the cluster scheduling engineer, the one wrestling with managing these complex workloads, often across different clouds and hardware types.
Yeah, and for this dive, we pulled together some really powerful source material. We've got proprietary insights on how giants like Netflix handle cloud efficiency at, hyperscale. We've also got a case study digging into massive GPU cost savings using Kubernetes spot instances, some academic reviews looking at next-gen cost-aware, even carbon-aware scheduling, and some deep architectural analysis of multi-cluster orchestration, stuff that stretches all the way from the central cloud out to the edge.
Okay, so let's unpack this. The mission here is figuring out how the best organizations manage to balance that breakneck speed of innovation with, well, basic financial prudence, especially now with these huge demanding AI workloads. And we have to start at the root, right? The FinOps imperative.
Right. The first problem, really, for that cost ops analyst is the cloud bill shock itself. And AI workloads just make this so much worse. The cost drivers are pretty obvious. First, you're running premium hardware GPUs, TPUs, which have a high unit cost, and often you're running them nonstop for long periods, like during intense model training. Second, the way billing usually works is retrospective. You spend the money, you commit the resources, and you only really find out the true cost maybe a month down the line.
And often, the organization itself just isn't set up to handle this properly. I mean, our sources really highlight this core barrier. You've got finance teams controlling the budgets. They need predictability, right? But then you have the engineering teams controlling the actual architecture, the speed of iteration. And that gap between them, the mechanism to actually connect real-time engineering usage with financial accountability, it's often just missing.
Exactly. And that organizational disconnect leads straight to what we see is a pretty severe FinOps maturity gap. FinOps is definitely a growing field, but most teams are still quite narrowly focused. They're cleaning up day-to-day operational issues like finding forgotten VMs or something. They're not really driving strategic financial architecture. And here's the real kicker. One survey found only about 2% of organizations actually integrate their cloud spending, their SaaS spending, and this rapidly growing generative AI spending into one unified view. If you can't even unify the basic data model underneath it all, how can you possibly manage it strategically? Your capabilities just stay siloed and, frankly, ineffective.
Okay, so if the core problem is that data fragmentation, that organizational split, how does a company operating at the kind of scale Netflix does? I mean, they rely massively on AWS. How do they get a handle on this efficiently? You mentioned their solution boils down to democratizing curated data.
That's the heart of it, yes. They essentially shine a massive spotlight on usage and cost patterns, making it visible across literally hundreds of independent engineering teams and microservices. It's all about transparency driven by data.
And their platform data science engineering team, the DSE team, built a specific solution.
Yeah, a two-component solution designed precisely to handle this massive complexity in a scalable, consistent way. Honestly, this setup is kind of the blueprint for any effective cost ops analyst function out there.
Okay, so component one is the foundational platform data, or FPD. What is that exactly?
Think of FPD as the absolute single source of truth for cloud usage within Netflix. It's a centralized data layer, and it has a really consistent data model covering three key pillars. Inventory, so what resources actually exist. Then ownership, which team or service owns each resource. And finally, usage data, how much of that resource is being consumed.
And you mentioned something critical here, data contracts. That sounds important for tackling that inconsistency problem across different teams.
It's absolutely crucial. It's more than just like a verbal agreement. It's a technical guarantee enforced by the platform. Platform producers may be the team running the Spark platform or the Kubernetes control plane team. They must adhere to a strict schema when they submit their cost-related data into FPD. This contract forces data quality and consistency. It stops different teams reporting essentially the same resource consumption but using incompatible formats or metrics.
Okay, that makes sense. So you have this clean, reliable foundation, the FPD. What sits on top of that?
That's where the second component comes in. The Cloud Efficiency Analytics Layer, or CEA. This is where the magic really happens for the cost ops analyst. CEA takes that raw, standardized FPD data and applies quite sophisticated business logic to it. Its main job is to produce the key output everyone needs: accurate cost figures and, critically, ownership attribution, calculated at whatever granularity is needed, maybe down to the minute for some services, or rolled up across the whole org.
And the main goal there is transparency, especially with shared resources.
Exactly. Because modern cloud infrastructure is just inherently multi-tenant, right? You might have one massive Kubernetes cluster or a complex data pipeline being shared by maybe 10, 20 different services or teams. The costs for that shared infrastructure have to be distributed accurately and fairly. So CEA compartmentalizes the data. It makes sure that when a downstream consumer, like an engineering team lead, sees a cost show up under their team's name, they understand exactly why that slice of the shared resource was attributed to them. And crucially, they understand how that calculation was actually performed. There's no black box.
Wow, that level of transparency must change the culture quite a bit. It stops being about finance pointing fingers at engineering, maybe.
Precisely. It shifts the whole conversation. It moves towards engineers actually self-governing their usage because they can see the impact directly. They can't really hide utilization behind some vague line item on a massive bill anymore.
And this leads us straight to what you called the most fundamental FinOps guardrail, especially for these big, complex AI environments, whether it's in a large company or even a government agency setting.
Yeah, tagging and attribution. It sounds basic, but it's absolutely essential. If every single cloud resource isn't immediately and correctly tagged with the project,
Yeah.
the environment, the owner, you instantly fall into that all too common trap where nobody owns this cost.
Mm-hmm.
That granular tagging is the fundamental technical enabler for making something like Netflix's CEA attribution actually work in practice.
Okay, so tagging gets you attribution. But beyond that, the cost ops analyst still faces a huge challenge just forecasting AI costs, right? Because the workloads themselves are just so unpredictable. New experimental models, sudden bursts in usage, maybe massive retraining efforts kicking off.
Absolutely. Forecasting AI is notoriously difficult. The FinOps guidance here is pretty clear, though. You must mandate a clear separation of costs. You have to draw a line between R&D and experimentation costs, which are, by nature, often time-bound, erratic, reflecting that fast iteration cycle, and your production costs, which ideally should eventually settle into more predictable, stable patterns. If you mix those two buckets together, that volatile experimental spending just completely blurs your true cost per user or cost per transaction, whatever your key metric is. It makes any kind of strategic budgeting almost impossible.
Makes sense. And to manage all this data, the attribution, the forecasting, the cost ops analyst need specific tools, right?
Yeah, they definitely rely on specialized instruments. We saw mentions of commercial tools like IBM Cloudability that focuses a lot on predictive analytics, helping set those budgets and forecasts. There's CloudKeeper, which seems more specialized in identifying specific optimization and savings scenarios, and then tools like Kest AI, which are really tailored for the dynamic world of Kubernetes and containerize AI workloads, offering both forecasting and optimization features. These tools are pretty much indispensable for taking that standardized attribution data we talked about and turning it into actionable cost strategies.
Okay, so let's shift perspective now, moving from the financial layer down to the architectural layer, where the framework maintainer lives. Their big battle seems to be this massive GPU cost bottleneck. You mentioned even for mid-sized AI companies, seeing cloud GPU bills shoot past $20,000 a month isn't unusual, and often maybe unnecessarily so.
That's right. It's a major pain point. A lot of companies, especially when they're starting out or moving fast, they turn to managed AI services, things like AWS SageMaker or Azure ML. They offer simplicity, speed of deployment, which is attractive.
Sure, seems like the easy path. But you said these often become growth bottlenecks later. Why are these managed services often so inefficient from that framework maintainer's perspective, the person trying to control the actual costs?
It mostly comes down to really poor utilization. We consistently see average utilization rates for GPUs in these managed services, hovering somewhere around maybe 20%, sometimes even less.
20%, that's incredibly low. Why is it happening?
Well, it's partly because managed services abstract away so much complexity. To handle potential peak capacity, they often force you or strongly encourage you to over-provision. Plus, they can sometimes suffer from slow cold start times. So if you try to be aggressive and scale down to zero to save money, the time it takes to spin up new GPU capacity when a burst of traffic hits might be totally unacceptable for the user experience. So what happens? The framework maintainer feels forced to keep these really expensive GPU resources warm, just idling, waiting. And that results in immense waste.
Okay, so that pushes people towards taking more control. And this brings us to probably the core technical lever for optimization here, Kubernetes, or K8s. The case study you looked at showed some really striking results, didn't it? Migrating AI and ML workloads to self-hosted Kubernetes in the cloud, and then really leaning into GPU spot instances.
The savings were huge. We're talking potential annual savings exceeding $300,000 in that specific case, and up to an 80% reduction in the overall GPU computing costs. It's a game changer, but it requires effort.
Let's quantify that a bit more. The cost per query comparison was pretty stark.
It really paints the picture. So using the example figures, if you start with a managed service, maybe your cost is around text 2 USD per query. Just switching that workload to a self-hosted Kubernetes solution using standard on-demand GPUs immediately drops that cost down to roughly text 05 USD per query.
Wow. Okay, so that's a 73.5% saving right off the bat, just by taking control of the orchestration layer.
Exactly. But the real optimization, the really dramatic savings, come when you start playing the market dynamics, specifically leveraging spot instances.
Right, the significantly cheaper but potentially preemptible instances.
Yeah. By implementing a pretty aggressive, say, 80-20 split, running 80% of your GPU capacity on those cheaper spot instances, and keeping 20% on demand for stability and critical tasks, the cost of the case study plummeted further, down to about 10 var 008 USD per query.
0.008, that's a massive drop. Compared to the starting point with the managed service, that's a 90.7% saving.
That 90% figure, that's kind of the holy grail for the framework maintainer focused on cost.
Yeah.
And this is a big but, achieving it isn't trivial. It requires executing a pretty demanding framework built around 3 core technical steps.
Okay, that 90% savings sounds fantastic on paper, almost too good to be true. Let's inject a bit of skepticism. What about the operational cost? Isn't there a huge hidden cost there? I mean, moving from clicking buttons in a managed service console to actually managing a complex Kubernetes cluster yourself, keeping the infrastructure patched, dealing with spot instance interruptions, that needs highly specialized, expensive engineering time, doesn't it? Doesn't that labor cost from your framework maintainer team eat into those big financial savings?
That is absolutely the essential trade-off, and it's exactly why that framework maintainer role becomes so critical and needs strong skills. You're spot on. The first step, just adopting K8s and building that self-hosted replacement for the managed service, that's already a major engineering investment. But it's really the second step, properly utilizing spot instances, that introduces the heavy operational complexity you're talking about. You can't just flip a switch and hope for the best. You absolutely must build sophisticated, resilient interruption handling into your architecture.
Okay, so what does resilient interruption handling actually mean in practice for, say, a long-running AI training job?
It means the framework maintainer has to design and build systems that can, for example, rapidly checkpoint the model's state during training, like saving progress very frequently. Then, the system needs to detect the preemption warning signal from the cloud provider. You usually get a very short notice, maybe 2 minutes, sometimes less. It has to immediately save the final state upon receiving that signal. And then, crucially, it needs automation to automatically reschedule that interrupted workload onto a replacement spot instance if one is available, or perhaps fall back temporarily to a more expensive on-demand instance if needed. All of this with zero data loss and minimal delay to the overall job completion time. That requires dedicated control plane logic, robust underlying data storage for those checkpoints. It's significant engineering. That 90% saving figure is only truly viable if the ongoing operational cost of building and maintaining that resilience layer is substantially less than the savings you get from using Spot. And that generally only holds true once you reach a certain scale of usage.
Right, scale matters. Okay, so that covers adoption and spot instances with resilience. What was the third step for the framework maintainer?
The third step hinges on smart workload optimization and scheduling within Kubernetes. This means implementing things like priority-based smart auto-scaling, not just scaling on basic metrics, but understanding which jobs are more important. and critically, implementing the concept of scale down to zero during idle periods whenever possible. If a queue is empty, the GPU should ideally be turned off completely. That prevents any possibility of paying for truly wasted idle capacity.
Avoiding over-provisioning is key, clearly. But you mentioned optimizing GPU usage is actually harder than optimizing CPU usage. That sounds like a trap many framework maintainers might fall into.
It definitely is. It's a common pitfall. When you're monitoring CPU utilization, you're often just tracking one or maybe two key metrics, like overall percentage used. Pretty straightforward. With the GPU, it's more complex. You really have to monitor multiple distinct components simultaneously to get the full picture. You need to look at the actual compute utilization of the processing cores, you need to look at the GPU memory usage, and you need to look at the memory bandwidth, how fast data is moving on and off the chip.
Okay, so what's the classic failure mode then? Where does it go wrong?
The classic scenario we see is something like this. The GPU memory usage might look really high, maybe 90% or more. Looks busy, right? Because a large model is loaded into the GPU's memory. But if you look deeper, the actual compute cores might be sitting idle for, say, 70% of the time. Why? Because they're just waiting for the input data pipeline to feed them the next batch of data to process. So the GPU is technically full, its memory is occupied, but it's not actually busy doing useful work most of the time. This kind of situation is exactly where that industry-wide estimate comes from, the one suggesting that $60 to 70% of the average company's GPU budget is effectively wasted on idle resources.
60 to 70% waste. That puts the business value of optimization into sharp focus. If a framework maintainer can successfully boost that utilization from, say, a typical 30% up to something like 80%, they've effectively, more than doubled their usable infrastructure capacity without buying a single new piece of hardware.
Exactly. The numbers we see are pretty consistent. Every 10% improvement in GPU utilization typically yields somewhere between a 15% and 20% reduction in cost for that workload. This reality pushes the smart framework maintainer towards employing more strategic optimization tactics, going beyond just basic auto-scaling.
Okay, let's break down those tactics. Tactic number one you highlighted was optimizing the data flow itself. Co-locate compute and storage.
Right. Data needs to get to the GPU incredibly fast. If your primary data storage is, say, network attached and physically or logically too far away from the GPU node, that network latency inevitably becomes the bottleneck. It stalls the very expensive GPU you're paying for. So the solution is fundamentally architectural. It means designing your setup to deploy high-speed storage, like local NVM drives, directly on the GPU nodes themselves. Or, if sharing data, ensuring extremely high-speed, low-latency interconnects like NVLink or InfiniBand between the nodes in the same training cluster, minimize those bottlenecks.
Okay, tactic two, distributed training. How do we split these huge AI workloads optimally across multiple GPUs?
Well, this really depends on the specific challenge you're facing with the workload. If you have a absolutely massive data set that just needs to be processed faster than a single GPU can handle, you typically use data parallelism. You basically split the input data across multiple GPUs, and each GPU processes a portion of it using a copy of the model. On the other hand, if your primary challenge is an enormous model, maybe a foundational model with billions of parameters that's simply too memory constrained to fit onto a single GPU's VRAM, then you use model parallelism. You actually split the layers of the neural network itself across different GPUs. The framework maintainer's job is to choose the appropriate method, or sometimes even a hybrid approach, and then carefully optimize the communication fabric between those GPUs to make sure they aren't spending all their time waiting for each other. That communication overhead can kill performance if not managed.
Got it. And tactic three seems to address that fundamental timing issue, the GPU waiting for data, preload and cache data.
Yeah, this is critical. A $20,000 GPU is essentially a very fast, very expensive waiting machine if its input data pipeline is slow or inefficient. The framework maintainer has to focus on implementing techniques like asynchronous data loading. This means the process of fetching and preparing the next batch of data runs in parallel, on the CPU perhaps, while the GPU is busy computing the current batch. You also need to aggressively prefetch the data that you know will be needed next and potentially cache frequently accessed data closer to the GPU. The goal is to keep that execution pipeline consistently full, ensuring the GPU is always busy crunching numbers, not waiting for I/O. It really shifts the focus from just provisioning resources to actively managing the efficiency of the entire data throughput pipeline. #3. Intelligent scheduling and heterogeneity. the cluster scheduling engineer's challenge.
Okay, so this whole quest for maximum utilization, minimum cost, it ultimately lands squarely on the shoulders of the cluster scheduling engineer, doesn't it? We're definitely moving way beyond simple placement algorithms now. You mentioned that traditional scheduling mechanisms, the ones we've used for years, are kind of breaking down in today's cloud environment. Why is that?
Primarily because they were designed for a much simpler, more homogeneous world. They generally assume standard CPU architectures, maybe running in a single data center, probably with relatively static pricing for resources. Today's reality is just wildly different. We're dealing with intensely heterogeneous clouds. You've got AWS, Azure, GCP, maybe even private cloud bits, all offering different types of GPUs, different generations, vastly different spot market pricing that changes by the minute, different network topologies between regions. And on top of that hardware diversity, you have dynamic factors like real-time energy prices becoming relevant, or specific software interoperability requirements between tasks. Traditional schedulers are just not built to be cost-aware or context-aware at that level of complexity. They lack the necessary inputs and logic.
So the goalposts have moved. The objective of cost-aware scheduling isn't just place this container on an available node anymore. It's much bigger. It's about sequencing and assigning the entire ML pipeline. The pre-processing steps, the main training job, the validation phases across potentially globally distributed resources in a way that minimizes the total spend while still strictly meeting performance and usability requirements, the SLAs.
Exactly. And to achieve that complex optimization, modern scheduling frameworks are starting to incorporate AI techniques and much more advanced cost prediction strategies. We're seeing broadly two dominant advanced strategies emerge, but each comes with pretty significant trade-offs that the scheduling engineer has to carefully consider.
Okay, let's tackle the one that sounds the most cutting edge first. Reinforcement learning, RL-based scheduling. How does that work?
Right, so an RL-based scheduling system, maybe one using something like evolutionary reinforcement learning, it doesn't operate based on a fixed, pre-programmed set of rules like always prefer spot instances unless latency is critical. Instead, it works on a feedback loop. It makes a scheduling decision, for instance, that might try placing a specific training job on a very low-cost spot instance that happens to have higher network latency to the data source. Then it observed the outcome. What was the actual cost incurred? What was the actual latency achieved? Did the job complete successfully? Based on that outcome, it receives a reward if it was a good decision, or a penalty if it was bad. Over time, through many, many such trial and error executions, it uses this feedback to dynamically learn and adapt its scheduling policy. It essentially teaches itself the optimal way to balance cost and performance for the specific patterns of your workloads.
So it learns the ideal trade-offs specifically for your environment. Sounds powerful. But what's the catch? What's the complexity there?
The trade-off, and it's a really significant one in practice, is its dependence on data. RL algorithms typically require extensive training data. We're talking potentially hundreds or even thousands of past execution trials before they converge on a truly optimal scheduling policy. This means that cold start scenarios, like when you introduce a completely new type of workload or onboard a new customer with unique requirements, can lead to pretty poor scheduling performance initially. There's this inherent delay before the scheduler becomes genuinely effective. The cluster scheduling engineer has to actively manage and mitigate this initial period of potentially suboptimal delayed convergence.
Okay, data hunger is the challenge for RL. What's the second major advanced strategy?
The second direction involves incorporating more explicit external constraints into the scheduling decisions, specifically energy-aware scheduling. This is gaining traction fast. The focus here shifts partially towards power efficiency. Some systems even use techniques like thermal-aware task migration, actively moving workloads off compute nodes that are running too hot to save power or prevent thermal throttling.
That makes sense, especially with the increasing focus on sustainability and the environmental impact of large AI models. But does it create conflicts?
It immediately creates a potential conflict, yes.
Yeah.
The greener node may be one that uses less power per computation, or perhaps is located in a data center powered primarily by renewable energy sources, might not be the node that offers the absolute best raw compute performance for that specific job. Choosing the greener option might introduce slightly higher network latency to access data, or just take longer to complete the computation. This forces the scheduler into a much more complex balancing act. Its objective function suddenly becomes multidimensional. It's trying to minimize some combination of cost plus carbon footprint while simultaneously maximizing performance and reliability. It's a much harder optimization problem.
Right. Now, stepping back to the bigger picture, These complex ML pipelines, they're rarely confined to just one data center anymore, are they? You mentioned global optimization and workflows spanning multiple data centers, maybe even multiple cloud vendors, these truly heterogeneous cloud environments. This seems especially true for things like real-time analytics or processing massive IoT streaming data feeds.
Absolutely. That global scope is becoming increasingly common, and it introduces some really serious geo-distributed scheduling challenges for the engineer. The schedulers suddenly can no longer afford to ignore three massive cost and performance factors that were less critical in a single region setup. First, obviously, network latency between different geographic regions or different cloud providers. Moving data takes time and impacts application responsiveness. Second, the potential necessity of data duplication. For resilience or performance, you might need copies of large data sets stored in multiple regions, which incurs storage costs. And third, perhaps the most overlooked but often crippling cost, data egress charges. Moving large amounts of data out of one cloud provider's network, or even sometimes just out of a specific region within the same provider, can be prohibitively expensive depending on the pricing model. The scheduling engineer needs access to real-time price feeds, not just for compute, but for interregion networking and storage egress costs as well.
It sounds incredibly complex. But this geo-distributed approach isn't just about trying to find the absolute cheapest compute somewhere on the globe, is it? It's also fundamental for resilience, for fault tolerance.
Exactly. It's often essential for achieving high availability. Geodistribution facilitates fault tolerance through techniques like redundancy-aware replication.
Right.
Think about something critical like recommendation engines' real-time inference models.
Mhm.
You absolutely need replicas running in multiple regions or availability zones
Mm.
so that if one fails, the service remains available.
But that reliability, that redundancy comes at a direct financial cost, right? More running instances, more data sync.
It absolutely does. And this leads to the scheduler's ultimate dynamic decision-making challenge. When a failure is detected in one region, or perhaps when local resource pressure spikes unexpectedly in one cluster, the cluster scheduling engineer's framework, the sophisticated scheduler, has to decide in real time precisely when and where to instantiate those necessary replicas. It needs to balance the imperative of maintaining service reliability against the additional financial expense of spinning up and running that redundancy. This demands a system that is continuously monitoring, learning, and adapting to the current global state of resources, costs, and workload demands. It's a high-stakes, real-time optimization problem. Hashtag KEG4. Orchestration in the cloud-to-edge continuum. Framework maintainer scheduler focus.
Okay, and the complexity dial just keeps turning up, doesn't it? When we factor in the rapid rise of edge computing, placing compute resources much closer to the end users or data sources for lower latency, this creates a whole new architectural reality. It seems to demand a new breed of orchestrators, ones capable of bridging that gap between the relatively standardized centralized cloud environment where Kubernetes is largely the default, and these highly decentralized, often resource-constrained, unstable, and very heterogeneous edge environments.
Precisely. This is the challenging domain of multi-cluster cloud edge orchestration, often abbreviated as MCCEO. And the requirements placed on these orchestration systems are pretty extreme, simply because you're trying to seamlessly manage two fundamentally different worlds. For the framework maintainer designing such a system, resilience is absolutely paramount, maybe even more so than in the cloud. The architecture must support robust fault tolerance and high availability. A critical requirement is that if the centralized route management component fails or becomes unreachable, the individual edge clusters must have enough autonomy to know exactly which critical deployments to initiate or maintain on their own.
Yeah.
They can't just sit there waiting for instructions that might never come.
Okay, resilience first. And scalability must be non-negotiable too, right? Especially if you envision potentially thousands of edge locations.
Absolutely. An effective MCCEO system has to handle the seamless addition of potentially hundreds or even thousands of edge clusters without any significant performance degradation in the central management plane. And critically, auto-scaling needs to work effectively at both levels. Scaling the resources within an individual edge cluster, the workers, and potentially even auto-scaling the number of clusters themselves based on demand or geography.
And the third key requirement you mentioned.
Infrastructure independence. This is huge at the edge. Edge devices are inherently diverse. You'll find a mix of hardware architectures, traditional by 86, power-efficient ARM, maybe specialized AI accelerators. You'll have varied software stacks, different operating systems, and crucially, you have to assume unstable, sometimes low-bandwidth network conditions, which are typical of many last-mile edge deployments. The orchestrator has to function reliably across all this diversity.
So we're seeing specialized orchestration tools emerging to tackle this multi-cluster, cloud-to-edge reality. For the cluster scheduling engineer trying to manage this, you highlighted a couple of prominent names.
Yes. Two names frequently come up in this space. First is Karmata, which is also known as Kubernetes Armada. It's a CNCF Cloud Native Computing Foundation incubation project, specifically designed for multi-cluster and multi-cloud Kubernetes management. Karmata typically uses a centralized hub cluster to manage and synchronize configurations and application deployments across multiple member-subordinate clusters. It offers quite robust features needed for this model, like multi-cluster service discovery, ingress management across clusters, and capabilities for cross-cluster application failover.
Okay, Karmata from the CNCF, and the second one.
The second one is kubeadmiral. This was originally developed by ByteDance, interestingly, as a successor to an earlier multi-cluster project called KubeFed. kubeadmiral's particular focus seems to be on more advanced scheduling capabilities, including the ability to dynamically reschedule workloads between clusters based on changing real-time conditions like shifts in resource availability, cost fluctuations, or policy changes. That dynamic rescheduling aspect is really vital in volatile cloud and edge environments.
Now, managing all this complexity, orchestrating across potentially thousands of locations, it sounds powerful, but it must come with some hidden cost, right? Some overhead.
Absolutely.
Yeah.
And to understand those hidden costs, the price you pay for that architectural flexibility. Our source material included a really critical case study. It looked at the integration of a dedicated edge orchestrator called Orchestra with standard Kubernetes clusters, creating a model they called K-Orchestra. This integration is a perfect example of that fundamental trade-off. Achieving sophisticated cloud-to-edge orchestration introduces a definite, measurable management overhead.
Okay, let's dig into that integration model. How does this edge orchestrator Orchestra actually manage the Kubernetes clusters it treats as child clusters?
The core component is the Orchestra agent. This agent is deployed and runs as a pod inside each of the managed Kubernetes clusters. It has two primary responsibilities. First, it listens for and forwards deployment requests coming down from the centralized Orchestra root component. Second, and this is key for the overhead discussion, it constantly transmits granular resource utilization updates from within the Kubernetes cluster back up to the Orchestra root. By default, the study noted it does this every 2 seconds. It pulls this utilization data using the standard Kubernetes metrics API available within the cluster.
Every 2 seconds. That constant chatter definitely sounds like a potential source of overhead. So let's look at the overhead metrics from the study. They compared K-Orchestra against competitors like Karmata and another system called Open Cluster Management, OCM, running on an idle 6-node Kubernetes cluster, which seems like a fairly typical small edge or development setup. The cost ops analyst definitely needs to budget for this management layer itself. What did the CPU comparison show?
The results were pretty clear. The comparison revealed that K-Orchestra consistently had the highest CPU utilization, specifically for its own internal management plugin components. It registered around 0.017292 CPU seconds per minute on average just for the management layer. That was measured to be 4 times higher than the CPU overhead imposed by Karmata under the same idle conditions.
4 times higher CPU usage just to manage the cluster even when it's idle. Where did the study suggest that extra load was coming from?
The primary culprits identified were twofold. First, the architectural choice of using MongoDB within the central Orchestra root component seemed to contribute significantly. Second, and perhaps more impactful, was the sheer frequency of the Orchestra agent's constant metrics querying, hitting the Kubernetes metrics API every 2 seconds from within each cluster, collecting the data, processing it slightly, and transmitting it back up that creates a consistent measurable CPU strain on the host nodes, even when no user workloads are running.
Okay, CPU overhead is notable. What about memory usage? Were the figures there alarming too?
They were arguably even more striking. The study found that K-Orchestra consumed, on average, $296.39 text-to-mainnet of memory just for its management components running within the Kubernetes cluster.
Nearly 300 megs. How did that compare?
That was calculated to be 9.99 times more memory than Karmata consumed under the same idle conditions. For a small edge node, maybe an industrial PC or a constrained device where memory resources are often very tight, dedicating almost $300 of RAM just to the management overlay before you even run your actual application is a really significant operational cost to factor in. The analysis suggested this high memory consumption was largely due to a specific component called the Node Net Manager running on every single node, combined with the memory footprint of the underlying MongoDB dependency used by the root.
Wow. Okay, so if I'm that framework maintainer designing an edge appliance or system, I literally have to account for potentially hundreds of megabytes of management overhead before I even deploy the first real workload. That's tough. Did the network traffic also increase?
It did. The study measured that K-Orchestra generated approximately 1.9 times more idle network traffic compared to a vanilla, unmanaged Kubernetes cluster baseline. That extra background traffic was attributed primarily to the internal communication needs of the Orchestra agent, constantly sending metrics upstream, plus the chatter from the various network components necessary to reliably bridge the centralized cloud route with the distributed edge clusters. In edge environments where network bandwidth might be limited, metered, or expensive, this constant background traffic is another non-trivial operational cost.
And finally, the deployment time comparison seemed to confirm this overhead story, deploying 100 simple services.
Right. Vanilla Kubernetes as the baseline was the fastest, taking about 36,333 total text ms around 36 seconds total time to get all 100 services deployed and scheduled. K-Orchestra, managing the same deployment across its structure, took significantly longer, 76,666 text, so over double the time, about 77 seconds.
And where was that extra time being spent?
Critically, the analysis pinpointed that the majority of the delay introduced by K-Orchestra occurred specifically in the phase between the deployment request being accepted and the corresponding pod actually being scheduled onto a node, deployed to pod scheduled phase. This clearly isolates the time cost associated with that intermediary Orchestra root component, having to receive the request, make its cross-cluster scheduling and placement decisions based on the potentially slightly delayed metrics data it has, and then relay the instructions down to the target Kubernetes cluster via the agent. It vividly demonstrates that the necessary complexity required for achieving that sophisticated global orchestration comes with a measurable, significant performance penalty and resource consumption overhead. That overhead absolutely has to be factored into the total cost of ownership calculation by the cost ops analyst and the framework maintainer. So whether an organization goes all in on complex multi-cluster orchestration like K-Orchestra, or focuses on mastering GPU spot instances within a single cluster, the fundamental enemy that keeps cropping up is resource waste. It's the common thread. Our source interviews really confirm this fundamental behavioral pattern. Developers, generally speaking, prioritize speed and convenience above almost everything else. Getting features out the door is paramount. Cost optimization. It often simply isn't a high priority for them unless the cloud bill suddenly becomes unexpectedly high, which means, in practice, that serious cost monitoring and optimization efforts often only happen reactively, in response to some kind of billing anomaly or budget overrun.
Yeah, changing that default developer mindset is definitely tough. But the experts interviewed seem to view implementing mandatory continuous waste monitoring as a highly useful, perhaps even essential tool. And the motivation seems twofold.
Exactly. It's driven by twin incentives. First, the obvious and direct reduction in cloud costs, which appeals to finance and management. Second, the increasingly important organizational focus on reducing environmental impact. Wasted compute cycles mean wasted energy, which has a carbon footprint. So waste monitoring hits both financial and sustainability goals.
Okay, so if an organization decides to build or implement a dedicated waste monitoring system, what does that architecture typically look like?
The sources suggest a fairly standardized architectural approach. First, the system absolutely must integrate seamlessly with the native monitoring tools provided by the cloud platforms themselves, things like AWS CloudWatch, Azure Monitor, Google Cloud Monitoring. It needs to pull out both the fine-grained utilization metrics, CPU, memory, GPU usage, network I/O, etc., and also the necessary configuration and topology data, instance types, regions, tags, dependencies from these native sources.
Okay, so it gathers the raw data. Where does that data go?
It typically feeds into a central data processor component. This processor's main job is to perform the calculations needed to derive the two key metrics that really matter. These are the metrics designed to translate raw engineering activity into a language that the cost ops analyst and business stakeholders understand.
And those two key metrics are?
The first crucial metric is the waste ratio. This aims to formally quantify the amount of resource waste for a given service or application. It's typically calculated based on the difference between the capacity provisioned, so what the team requested or configured, like the size of the VM or the number of pods, and the actual utilization measured over time. However, crucially, a good waste ratio calculation doesn't just penalize all unused capacity equally. It strategically accounts for a predefined threshold or slack. This is the amount of headroom the team explicitly deems necessary for handling sudden bursts or allowing for rapid auto-scaling without performance degradation.
Okay, so waste ratio accounts for necessary slack. What's the second key metric?
The second metric is potential savings. This is often the one that gets management's attention most effectively. It takes that somewhat abstract waste ratio percentage and converts it directly into a concrete monetary value. For example, potential savings per hour or potential savings per service per month. Expressing the waste in dollars or euros, etc., creates a much clearer, unambiguous financial incentive for developers and their managers to actually take action to reduce that waste.
Makes sense. And for this system to be truly effective day to day, how should these results be presented?
For the system to be practical, the calculated results, the waste ratios, the potential savings, trended over time, absolutely must be stored in a time series database, like Prometheus, InfluxDB, etc. And then they need to be presented visually in an easily digestible dashboard. The core functional requirement here is clear visualization, showing potential savings trends over time, breaking down waste statistics by service, by team, maybe by project tag. The goal is to make the financial impact of inefficiency immediate, undeniable, and actionable.
Okay, but let's circle back to that tension you mentioned earlier, the inherent conflict between needing flexibility and avoiding waste. Framework maintainers, cluster scheduling engineers, they often need to intentionally over-provision resources sometimes, right? To maintain that slack for spiky, unpredictable AI workloads, or just to allow auto-scaling mechanisms to react quickly enough.
That is the absolute core structural tension in cloud cost management. You need slack for performance and reliability, but too much slack equals waste. Now, if the waste monitoring system allows users, maybe the developers themselves, to manually set their own utilization threshold, say, developer decides their service needs 70% slack just to be safe, effectively hiding significant underutilization below that threshold.
Then the system risks becoming useless, right? Users could potentially deliberately hide waste simply by setting their acceptable threshold ridiculously high.
Right, it defeats the purpose. So how do you introduce governance and prevent gaming the system without removing the flexibility engineers genuinely need? The proposed solution discussed in the sources is actually quite simple, but potentially brilliant in its impact. It relies on applying transparency not just to the waste itself, but to the threshold used to calculate it. The key is that the waste monitoring system must ensure that the specific utilization threshold being used for any given waste ratio calculation is prominently and clearly displayed right there on every graph and dashboard relating to that service.
Ah, okay. So instead of just showing waste ratio, 15%, the graph would explicitly say something like waste ratio, 15%, calculated based on a 20% reserve slack threshold set by Team Alpha.
Exactly. Displaying that threshold transparently means that every stakeholder looking at the data, the engineer who owns the service, the cost ops analyst trying to budget for it, the manager overseeing the team can immediately see and question whether that amount of reserve slack, the 20% in your example, is actually financially justified or architecturally necessary for that specific service's observed behavior. It subtly but powerfully shifts the conversation and moves away from a potentially accusatory, "Are you wasting resources?" toward the more collaborative and justifiable discussion. Is the amount of slack you've reserved here really appropriate for the service's actual load pattern and scaling needs? That transparency around the slack itself is the key to effectively managing that necessary intentional over-provisioning. Hashtag #Adoratra. So after digging through all this, what have we really uncovered in this deep dive? I think it's clear that truly mastering the cloud for these massive, expensive AI workloads requires a genuine synergy, a deep collaboration between financial operations and core engineering practices. We saw that the cost ops analysts absolutely need sophisticated data pipelines and attribution models, like the FBDCEA framework Netflix built, to move beyond just looking at lagging bills and get towards real-time, accurate cost attribution and insight.
Yeah, and the framework maintainer. They can achieve truly massive savings, like that potential 90% reduction, but only by embracing and mastering the significant operational complexity that comes with technologies like fine-tuned Kubernetes orchestration and the aggressive, resilient use of GPU spot instances. It really proves that the level of control you have over the infrastructure layer is directly proportional to your potential for cost efficiency.
And looking forward, the cluster scheduling engineer is clearly pushing the boundaries. They're moving rapidly towards much more intelligent, context-aware algorithms from those RL-based systems that learn optimal placement from past executions to potentially even carbon-aware systems that factor in environmental impact alongside cost and performance. All this is necessary to manage workloads across these increasingly complex, heterogeneous cloud and now edge infrastructures.
It feels like efficiency isn't just a secondary concern or nice to have anymore. It's becoming, or maybe already is, the primary architectural driver for many systems. And this trend seems to be relentlessly pushing innovation away from older monolithic apps towards more containerized, serverless, highly optimized, but also inherently more complex multi-cluster architectures. But as we saw really vividly in that KI customer case study, this necessary complexity comes with its own tangible cost, doesn't it? The management overhead required to achieve that ultimate flexibility and orchestration introduces significant CPU, memory, and network resource consumption that absolutely has to be factored in and amortized against the benefits you expect to gain.
That brings us perfectly to our final provocative thought for you, the listener, to mull over. We heard from industry experts in our sources that, fundamentally, cloud providers tend to profit when you, the customer, over-provision resources. They aren't always strongly incentivized commercially to proactively tell you when you're using a resource that's perhaps unnecessarily expensive or oversized for your actual needs. So the question is this. If these AI-driven scheduling frameworks, the ones the cluster scheduling engineer is building, become truly smart enough to automatically and ruthlessly minimize cost, while also rigorously enforcing maximum resource utilization, will the biggest remaining obstacle to achieving true financial efficiency in the cloud ultimately be the technological challenge of building these schedulers? Or will it be the potentially conflicting commercial business models of the cloud providers themselves? Where does the final bottleneck lie?